All right, welcome back to the deep dive. You know we're all about giving you that need-to-know info efficiently. No need to waste time, right?
Mhm.
You're busy, you want to stay on top of things, and you've sent over some really interesting stuff about this whole small language models thing.
Yeah, it's a really interesting question you've brought up. Is bigger always better in AI? That seems to be the trend with all these massive language models we hear about. But your sources make a pretty compelling case for smaller models making some serious waves. We're going to dive into all that, figure out if SLMs can actually hold their own against those giants.
Right, we want to see if they can compete or maybe even do things those massive models just can't. We've got a whole pile of research papers, articles, all sorts of sources here, so we can really get the full picture of what's going on with SLMs. Now, from what I'm seeing here, we're talking about models with something like 1 to 8 billion parameters, maybe up to 13 billion in some cases.
Yeah, that's the general range. But just to be clear, we're not talking about any simple AI that can just do one little thing. These SLMs, they need a solid foundation of reasoning and language understanding to handle multiple tasks, or at least one really complex task, really well. So let's get into it. Where should we start with exploring these smaller but mighty AI models?
I think a good place to start is with the different types of SLMs out there. Looks like we can group them into two main categories. Those that are task agnostic, aiming to be all-around language whizzes, and those that are specifically designed for a particular job. Let's start with the task agnostic ones. It wasn't so clear early on if a smaller model could ever really get all the nuances of language and reasoning like those big LLMs seem to. I remember that buzz around tiny stories, a 10 million parameter model that could generate coherent stories.
Oh yeah, that was a cool project. Definitely showed that smaller models can pick up on patterns in language, even with just a tiny bit of data. But to really get that deep understanding of language that can be applied across different tasks, like you were saying, you probably need a model with at least a few billion parameters. Tiny Stories was more of a glimpse into the potential of small models, rather than a direct competitor to those huge models when it comes to broad language skills.
All right, so moving up in scale, we have the Llama family, which has become a really important benchmark. Llama 2, which came out last year with its different sizes, quickly became the model to compare against, and they put it through that whole process. Initial training, then fine-tuning with labeled data, and finally reinforcement learning to make sure it aligns with human preferences. All that thanks to Meta's powerful research infrastructure. And then they evaluated it on like everything from coding to reasoning to just general knowledge.
Exactly, and it's interesting how often newer SLMs are benchmarked against Llama 2. Then came Llama 3 this year, again with various sizes, including an 8 billion parameter version, still an SLM, right? And the crazy part is the amount of data it was trained on, 15 trillion tokens. Compared to Llama 2's 1.8 trillion, that's a tenfold increase. Makes you think. Maybe the quality and amount of data are just as important as the size of the model, maybe even more so.
15 trillion. That's mind-blowing. What kind of improvements did we see with the 8B Llama 3 after all that training?
Oh, significant improvements everywhere. It got better at coding, better at reasoning, and it even got better at using external tools, and the benchmarks show it. The 8B Llama 3 actually beat out Gemma 9B and Mistral 7B on a whole bunch of tests. General knowledge, reasoning, coding, even math. Plus it's multimodal. It can understand not just text, but images, videos, and speech, too. Shows you what a smaller model can do with the right training data.
And it didn't stop there, right? The Llama 3.2 series. These are even smaller, at 1 billion and 3 billion parameters. And they're built to run directly on our devices.
Exactly. They're designed for stuff like summarizing text, following instructions, rewriting content, all on your phone or tablet. And what's wild is that they can still work with a huge amount of text, 128,000 token context window. Pretty big for models that small. Plus, they're designed to be efficient on all kinds of hardware you find in your gadgets. And get this, they perform really well for their size, top notch. And they come in quantized versions too, which means they need even less memory. It's all about bringing powerful AI to your fingertips. So for someone like you interested in mobile tech, this could mean way more advanced AI features right on your phone, even without an internet connection.
That's a really exciting glimpse into the future of mobile AI. And then there's Tiny Llama, a 1.1 billion parameter model, also based on that Llama architecture, but trained on a massive amount of data, like a trillion tokens. Again, a huge amount of data for a relatively tiny model.
It is, and Tiny Llama's got some really smart tricks up its sleeve. It uses rope E, which helps it understand the position of words in a sentence better. RMS norm for more stable training. SweetGLU, which is a more efficient activation function. And it's also got optimizations like GQA and flash attention, which make it process information way faster and more efficiently. Think of GQA like giving the model a better way to focus its attention, and flash attention makes it super fast at finding information, like searching a well-organized library instead of flipping through every page. It actually learns faster than other models that size. And there's Tiny Llama too, showing that these small models can even handle multimodal tasks and beat out some larger 7 billion parameter models.
So even though it's much smaller than Llama 2, Tiny Llama can get surprisingly close in performance on some benchmarks. And on some tasks, like answering true-false questions or multiple choice questions, it even does better than Llama 2, though it's not as good at really complex reasoning. Really shows that the relationship between model size and what it can actually do isn't always so straightforward.
Yeah, it's not a simple one-to-one thing. And then there's Mistral 7B. This model, it's built on the standard transformer architecture, but it manages to beat the larger Llama 2 with its 13 billion parameters on a lot of tasks. And it even beats Llama 34B at math and code generation.
That's pretty incredible for a 7B model. How does it do that?
Well, Mistral uses these techniques called grouped query attention and sliding window attention. They basically allow the model to handle information more effectively, so it's better at reasoning and understanding, especially with long chunks of text. And there's this interesting idea of effective size. They claim Mistral's effective size can be up to 38 billion parameters, depending on the task. It's like you have a really skilled carpenter representing that 7B model who can build a specific type of furniture just as well as a massive factory with tons of workers. That would be the 70B model. For that one piece of furniture, the carpenter is just as effective as the factory. But the factory can probably build a lot more different things.
Effective size. I like that. A useful way to think about it. So this 7B model can act like a much bigger model in certain situations, and Mistral also seems to have inspired a bunch of really interesting spin-offs.
It has. Zephyr 7B, for example, this one uses a technique called direct preference optimization, and it actually performs better than the original Mistral on some metrics for instruction following and conversation. And then there's this sparse mixture of experts version of Mistral. Basically, it's like 7 billion parameter models working together, and it's been shown to outperform Llama 270B and even GPT 3.5 on some tasks. When your sources were compiled, a lot of the top-performing models on the Open LLM leaderboard were built on this Mistral architecture. And then you have Eagle 7B, which uses a different architecture called RWKV. This one beats all the other 7 billion parameter models, including Mistral, when it comes to translating between languages. There's so much innovation happening at this scale, it's really exciting.
Wow, so many different approaches. Okay, we've talked about the Llama family and Mistral. What other task-agnostic SLMs are worth mentioning?
Well, there's the Phi series from Microsoft. Their first model, Phi 1, was all about generating code. And they did something really interesting. They trained it on a small data set, just 7 billion tokens, but they focused on making sure that data was super high quality. It was all carefully filtered code, synthetic textbooks, and exercises. Like we saw with Llama 3, it's not just about how much data you have, but also how good that data is.
So quality over quantity. And how did Phi 1 do?
It did incredibly well. This 1.3 billion parameter model actually beat out much bigger code models like Codex 12b and even huge models like Coder 540b and GPT 3.5, which has 175 billion parameters. This really shows that carefully selecting your training data can allow a much smaller model to do really well in a specific area. A classic David and Goliath story in the AI world.
That's amazing. And then Phi 1.5 took that a step further, expanding into areas like common sense reasoning and language understanding with another 20 billion tokens of synthetic data, all textbook quality, they call it.
Exactly. And Phi 1.5, still at about 1.3 billion parameters, got similar results to those much bigger models like Llama 2 7B, Falcon 7B, and Vicuna 13B on various common sense reasoning tests. Then they scaled up those ideas to create Phi 2, which is 2.7 billion parameters.
Yeah.
This one also did really well, almost as good as the much larger Llama 2 70B on a bunch of general language tasks.
And the Phi family keeps growing. There's Phi 3, which has models ranging from 2.8 to 14 billion parameters. The Phi 3 Mini, at 3.8 billion parameters, is doing a great job against those bigger models like Mistral and GPT 3.5.
Right. And Phi 3 is trained on an even better data set. They're using more filtered web data and synthetic content to make it more robust and safe. And then there's Phi 4, which is even bigger than the 14B Phi 3. It outperforms all the previous versions on different benchmarks. Big improvements in general knowledge, question answering, and math problem solving. It even beats Qwen 2.5 and a smaller version of GPT-4 on some reasoning and math tests. The pace of development here is incredible.
Yeah, it's moving fast. Okay, next up is the Orca series. They took a bit of a different approach, really focusing on improving reasoning abilities in smaller models.
Right, they noticed that just training on data generated by bigger models to get better scores on benchmarks wasn't necessarily making the models better at actual reasoning. So they came up with explanation tuning, where they used special instructions to guide the models to generate step-by-step, well-reasoned answers. The idea is to teach smaller models how to actually think like bigger models, like GPT-4.
So instead of just feeding it the answer, you feed it the whole thought process, right? Like showing it how to get to the answer.
Exactly. Using data from a project called FLNV2 and taking examples from ChatGPT and GPT-4, Orca, which has 13 billion parameters, managed to get almost 90% of ChatGPT's performance on really hard reasoning tasks. It even matched ChatGPT on another benchmark. It even did well on standardized tests like the SAT and LSAT. Pretty amazing for a model that's significantly smaller than ChatGPT.
Yeah, it makes you wonder if we've been too focused on making models bigger and not focused enough on making them smarter. And Orca 2 built on those ideas, right?
Yeah, Orca 2 was trained using even more advanced reasoning techniques and an even bigger and more diverse data set. And guess what? It outperformed those big models like WizardLM, which has 70 billion parameters, and the chat version of Llama 2, also 70 billion, on all sorts of tests: reasoning, math, general knowledge, safety, even truthfulness. It really shows the potential of teaching smaller models how to think, not just what to say.
So again, we're seeing that smart training data and targeted techniques can do wonders for smaller models. What about Google? What are they doing in the world of SLMs?
Google's got the Gemini series. They have some really big, powerful multimodal models in that series. But they also have smaller versions, Nano 1 and Nano 2. Those are 1.8 billion and 3.25 billion parameters, respectively. Even though they're small, they do really well with factual accuracy and information retrieval. And they can also handle reasoning, STEM subjects, coding, and multiple languages, plus different types of data like images and audio.
Multimodal at that scale? That's impressive. How do they pull that off?
They use something called knowledge distillation. Basically, the smaller models learn from the bigger Gemini models. They also use 4-bit quantization, which makes them more efficient in terms of memory. Gemini Nano 1 actually does better than those bigger models like USM and Whisper on a bunch of data sets. It's a very versatile model. Google also released Gemma with 2 billion and 7 billion parameter versions. These are open SLMs built using similar technology. And Gemma beats other similarly sized open models on a lot of standard text-based tasks.
So Google's definitely in the SLM game too. Now let's talk about Alibaba and their Qwen series.
Qwen's another big player. They have models ranging from 1.8 to 14 billion parameters, and they train them on a massive 3 trillion tokens of text and code. They're showing that with the right design and training, smaller models can compete with or even beat those larger models.
What are some of the key things they did to optimize their Qwen architecture?
They made several improvements. They found a better way to break down text into tokens. They made their models more flexible in handling relationships between words. They use a specific type of positional encoding that helps with understanding word order. And they've built in strategic biases in how the model focuses on different parts of the input. They also use a technique called pre-normalization, along with those efficient activation functions, and they've really fine-tuned the size of the internal processing layers. All these little tweaks help their smaller models get great results on benchmarks. For example, their 14 billion parameter Qwen model actually beat previous 13 billion parameter state-of-the-art models in general language understanding. Their code-specific model is really good at generating code. And their 7 billion parameter math model is almost as good as much bigger models at solving math problems.
And then they took it a step further with the Qwen 2 series, right?
Yeah, Qwen 2 has models from a very small 0.5 billion parameters all the way up to 72 billion. They've built on that original Qwen architecture with even more refinements. They've added stuff like grouped query attention and this new dual chunk attention mechanism, which is really good at handling really long sequences of text. The results are impressive. Even the smaller Qwen 2 models do great on challenging tasks. And their bigger models are either matching or beating those 30 billion parameter dense models, but they're only using a fraction of their total parameters at any given time. They can also handle really long contexts, up to 128,000 tokens in the bigger models. Again, shows you that clever design choices are just as important as making the model bigger.
We've talked a lot about models based on the transformer architecture, but I saw in the sources that there's some interesting stuff happening with alternative architectures too.
Yeah, there are definitely people looking at different ways to build models, going beyond just transformers. It's about addressing some of the limitations of transformers, especially when it comes to memory usage, efficiency, and just overall performance. State space models, or SSMs, are looking promising as an alternative or maybe a complement to those attention mechanisms in transformers.
Can you give some examples of these hybrid or alternative architectures?
Sure. There's Himba, which combines transformer attention and SSMs in a parallel way. Then there's Zamba, which uses a type of SSM called a Mamba model as its core, but they add shared global attention to it. Jamba mixes transformer and Mamba layers and even uses a mixture of experts design. And then there's Mamba itself, which is a pure SSM architecture that uses special algorithms that are optimized for hardware. Each of these is trying to get the best of both worlds, the capacity of transformers and the efficiency of SSMs.
It sounds like there's a lot of exciting research going on in model architectures. Okay, so we've looked at task-agnostic SLMs. Let's shift gears and talk about task-specific SLMs. The idea here is to train smaller models for a very specific purpose, sometimes even teaching them different ways to solve problems compared to a larger, more general model.
Exactly. Techniques like chain of thought prompting and knowledge distillation are really useful here. Let's start with math reasoning. We've got models like WizardMath 7B, which beats most open source models in the 7 to 40 billion parameter range on math problems, and WizardMath 13B, which actually beats the much larger Llama 270B on some really hard math data sets. They do this by focusing on teaching the model how to do the step-by-step reasoning needed to solve those problems.
So it's not just about memorizing answers, it's about learning how to think through the problem, right? And what about code generation? That's another area where we've seen some impressive results with smaller models.
Yeah, definitely. WizardCoder, which is specifically designed for code, does better than even those powerful models like Anthropic's Claude and Google's Bard on code benchmarks. Code Llama Python 7b beats the much larger Llama 270b on tests that specifically look at code generation. And Stable Code 3b, which is just 3 billion parameters, does just as well as Code Llama 7b, but on multiple programming languages. It's really all about specialization. Instead of having one giant model trying to do everything, these smaller, focused models show that tailoring the design and training data to a specific task can get you much better results, and it's way more efficient.
That's a huge gain in efficiency for code generation. And it's not just about creating new code, but also understanding and using existing code, right?
Right. SLaDe, which is a tiny model, just 200 million parameters, is really good at taking assembly code and turning it back into C code. It actually does better than those bigger models like Ghidra, ChatGPT, and even a neural network specifically made for this task. Pretty amazing. A model hundreds of times smaller, getting better results in a very specific area.
That's incredible. And what about things like machine translation? How are smaller models doing there?
We've got ALMA 13BR, a 13 billion parameter translation model that actually does better than GPT-4 and the winners of big machine translation competitions. It even beat those bigger models like NLLB 54B and GPT 3.5 in translating text between languages. And they're making it even better with techniques like contrastive preference optimization. There's even research showing that small pre-trained models, when they're fine-tuned for a specific area like translating medical text, can outperform those extra-large models.
So again, it seems like targeted training is much more effective than just going for the biggest model possible. And this task-specific approach is being used in a lot of different areas, right?
It is. We have SLMs like Flame, which is only 60 million parameters, but can beat those bigger models at making Excel formulas. And they're even being used as judges, like with the Prometheus model, to assess how good AI-generated content is. There's this trend of creating these very specialized SLMs for very specific tasks, and even competitions like BabyLM are pushing people to develop language models that can learn from very limited data. We're also seeing this in other areas, like generating images from text. Models like Segmine Stable Diffusion 1B, a distilled version of a much bigger model, can get great results with way fewer parameters.
So it's not just code, it's translation, it's Excel formulas, it's everywhere. These smaller, more focused models are proving to be really useful. Now let's get into how they're actually made. We've talked about some of the techniques already, like knowledge distillation. What else is there?
Well, we can group these methods into a few categories: basic training techniques, modular training, data strategies, and post-training optimizations. Let's start with the basic training techniques. The original way was imitation learning, where a smaller model learns by directly copying the outputs of a bigger model. But this had some problems. It didn't always generalize well to new situations, and it was very dependent on the quality of the data it was trained on.
But as we saw with those Orca models, the techniques have gotten much more sophisticated.
Yeah, Orca used something called progressive learning, where the smaller model learns not just the answer, but the whole thought process of a bigger model like GPT-4. The smaller model learns by looking at how the bigger model explains its reasoning step by step. Orca 2 showed that this approach can be very effective in getting the smaller model to think like the bigger model, even on really complex tasks.
And then there's explanation tuning, which is also important for those Orca models.
Yeah. Right. With this, you basically tell the bigger model to give you detailed explanations as it solves problems. By doing this, you give the smaller model much more information to learn from. Orca 2's ability to outperform those larger models, while also being less likely to hallucinate, really shows how powerful this technique can be.
Then there's knowledge distillation, which we talked about earlier. That's about transferring knowledge from a bigger model to a smaller one.
Yeah, KD has two steps. First, you extract the reasoning steps from a big language model, often using chain of thought prompting. Then you train the smaller model to not only predict the answer, but also to follow the same reasoning steps. Models trained with knowledge distillation often do much better than models trained from scratch or just by copying outputs. And there are even more advanced versions, like symbolic procedural knowledge distillation and the distilling step-by-step method, which have allowed smaller models to perform just as well as those much larger ones.
And there's also something called reasoning distillation, right? Which focuses on how to break down and solve complex problems.
Exactly. Decompositional distillation is where you have the big language model break down a complex problem into smaller, simpler subproblems. Then the smaller model is trained on those smaller problems. This has led to some really big improvements in performance on datasets that test reasoning. Even small 3 billion parameter models are outperforming bigger models on tasks like solving those grade school math problems.
And chain of thought knowledge distillation is another way to teach smaller models how to reason step by step.
Right. This involves fine-tuning the smaller model on examples of chain-of-thought reasoning that were generated by a bigger model. Because smaller models have limited capacity, this is often focused on one specific task. But researchers are trying different approaches like symbolic OTD and Socratic COT, which are aimed at making the reasoning more consistent and reliable.
So lots of really smart ways to teach smaller models how to think like the bigger ones. The sources also mention modularized training techniques. What's that all about?
That's about using combinations of smaller models, either through these things called blended ensembles or mixture of experts, MOE architectures. Instead of one giant model, you have multiple specialized parts that work together.
Kind of like having a team of experts, each with their own special skills.
Exactly. Blended ensembles, you're combining the outputs from multiple smaller models that were trained independently. The idea is to get a combined result that's as good as, or even better than, what a single, much bigger model would produce. Having different models with different strengths can often lead to more accurate and reliable predictions. There was even an example where a group of small models, 6 to 13 billion parameters each, outperformed that massive chat GPT in terms of user engagement for certain tasks.
That's a great example of how collaboration can be really powerful in AI. And what about mixture of experts?
MOE models, like that Mistral model we talked about before, have layers with multiple expert blocks. And then there's a router that decides which expert is best suited to process each part of the input data at each layer. Mistral has shown that it's better than models like Llama 270B at math, code generation, and multilingual tasks. And its instruction-tuned version even beats GPT 3.5 in human evaluations, even though it has fewer parameters that are actually active at any given time. It's like having a really big model where only the most relevant parts are switched on for each piece of information, making it much more efficient.
That's really smart. Okay, so we've got these smart training techniques and these modular designs. What about the data itself? How are people changing their data strategies to train SLMs effectively?
One big trend is using datasets generated by larger language models, synthetic datasets. The Tiny Stories project showed that you can train a really small model to generate fluent English stories using only synthetic data. Then there's the study that created Phi1. Textbooks are all you need. That study really emphasized using high-quality synthetic data to teach common-sense reasoning and general knowledge. And surprisingly, it ended up being really good at code-related tasks, even though the model was small. And the Tiny GSM project showed that a data set of math problems generated by GPT 3.5 could help a very small model get really good at solving math problems. It even rivaled the model that generated the data in the first place.
So instead of just using tons of raw internet data, people are creating more specific high-quality data sets, often using bigger AI models to help them do that. But those traditional data sets like Common Crawl, they're still important, right?
Yeah, they are. Datasets like the Pile, which has a huge variety of text from the internet, were used to train models like the Cerebrus GPT series. They're still a good foundation for training. But when you're training an SLM on synthetic data, a lot depends on the big model you use to generate that data, how good your prompts are, how diverse and robust the generated data is, and how well you filter it to make sure it's high quality.
Okay, so you've trained your SLM using these techniques and this high-quality data, but how do you make it even smaller and faster so it can run on devices with less power? That's where post-training optimization comes in, right?
Right. One big technique is quantization. It's all about reducing the precision of the numbers used in the model's weights and activations. This makes the model smaller and faster. So examples like SmoothQuant, which lets you quantize down to 8 bits without losing much accuracy, GPTQ, which is good for accurate low-bit quantization, and AWQ, which focuses on quantizing the most important parts of the model's activations.
So you're making the numbers that represent the model's knowledge smaller without making it any less intelligent. And then there's model pruning, which is another way to make it smaller.
Yeah, pruning gets rid of the parts of the model that aren't that important. Techniques like bilevel optimization can make the model really sparse, but it can still keep its accuracy, or even improve it. Human-in-the-loop pruning combines automatic methods with human review to make the model much smaller. And Shared Llama uses a very targeted approach, removing specific parts of the model. It also uses dynamic batch loading, so it ends up performing better than models its size while using much less computing power.
It's like carefully trimming away the fat to make it leaner and faster without losing its core functionality. And finally, the sources talked about using SLMs as draft models. What's the idea there?
That's a pretty clever way to make larger models faster. You use a smaller, faster SLM to generate a first draft of the output. Then, the larger model checks it and maybe fixes it. This two-step process can make the larger model a lot faster overall.
So the SLM is like a quick first pass, and the LLM is the quality control. Are there different types of these draft models?
Yeah, you have independent drafters, which are just smaller versions of existing architectures, and dependent drafters, which are more closely connected to the main model. Medusa and Hydra are examples of dependent drafters. They basically add multiple prediction heads to the main model so it can generate multiple possible next tokens at the same time. There are still challenges like making sure the draft model is fast but also accurate and making sure its output is something the bigger model would actually produce, but it's definitely a promising approach to making those big models faster. There are also some new techniques like dynamic adaptation and hybrid architectures that combine different approaches.
Sounds like a smart way to use both big and small models together. Okay, we've covered a ton about SLMs. Let's talk about some of the bigger picture takeaways from your sources. One thing I found interesting is that those task-agnostic SLMs, they seem to be doing amazingly well compared to LLMs that are like 10 times bigger. But we don't always know exactly why, except for that consistent theme of data quality.
Yeah, that's true. To try and understand this, there's this idea of effective size. Researchers are trying to figure out how big an SLM would need to be to match the performance of a much bigger model, like that 540 billion parameter Palm model.
So if a 7 billion parameter model performs just as well as a 70 billion parameter model on a specific task, we could say it has an effective size of 70 billion for that task. But there are some limitations with this idea, right?
Definitely. Effective size is usually based on the best possible performance of the SLM on certain benchmarks. It might not do as well on other tasks. And if we don't know the exact number of parameters in a model, we have to estimate the effective size based on what we know about its performance. So it's not a perfect measurement. But it's a useful way to think about how capable these smaller models are and how much more efficient they could be. And like we've been saying, the quality of the training data is really, really important. Whether it's carefully selected by humans or cleverly generated by bigger models, good data seems to be essential for getting those smaller models to perform so well, just like they emphasize the importance of training compute in that Palm paper.
And your sources also talked about those scaling laws that people have observed with large language models.
Yeah, those laws suggest that bigger models generally perform better. But the impressive results we're seeing with SLMs kind of challenge that idea. The authors of your sources think that those scaling laws need to be updated to include data quality as a factor. They even suggested a new equation with a term for data quality, though they admit it's hard to actually measure data quality in a really objective way. But it makes sense, right? No matter how big a model is, if it's trained on bad data, it's not going to do well.
Garbage in, garbage out, as they say. We've also seen over and over again how those task-specific SLMs can actually beat those big general models in their specific area of expertise.
Exactly. Like WizardMath, which is amazing at math, And Llama, which is a coding champ, they both outperform much bigger models on those specific tasks. Specialization is key. And a lot of the work on SLMs is driven by the need to have AI in places where resources are limited, like on mobile devices, in edge computing, or in places without reliable internet. The small LM family of models was specifically designed to be small and efficient enough to run on local devices. This could really change how we use AI, making it accessible in more places and to more people. And there's also research on running these smaller models on CPUs, which are more common and less expensive than GPUs. Techniques like quantization and sparsity are making that possible.
It sounds like while those big language models are getting all the attention, SLMs are a really strong contender. They strike a great balance between performance and efficiency.
Absolutely. This deep dive has really highlighted that smaller models are doing some really impressive things. They're challenging that idea that bigger is always better when it comes to AI.
And the keys to their success seem to be high-quality training data, well-designed models, and some really innovative training and optimization techniques. That's what allows them to be so efficient while still being super effective.
It's pretty exciting. It opens up a lot of possibilities for using AI in ways that are more accessible, more affordable, and use less resources, which could have a big impact on your life, both at work and in your personal life.
So after taking all this in, the big question is, what specific tasks or applications in your life could these smaller, more efficient models be really good for? And how do you see those big LLMs and those smaller, more nimble SLMs fitting together in the future? It's definitely something to think about.
We definitely